Imagine trying to predict exactly how, um, like, a brand new Lego set made of hundreds of different pieces will look and function just by knowing the individual bricks.
Yeah.
That's sort of the complexity scientists face with molecules, and it's absolutely crucial for breakthroughs in medicine, material science,
Yeah.
everything really.
That's a great analogy. Yeah. And for a long time, the best way, the most reliable way to do this has involved these incredibly complex calculations. It's almost like simulating every single atom in that Lego set.
Right.
And while they're powerful, these methods can be really, really slow, especially, when you get to even slightly larger molecules.
Okay, so these intricate simulations,
Yeah.
like density functional theory or DFT,
Yeah.
the research we're digging into today, neural message passing for quantum chemistry, it points out that even for like a pretty small molecule, maybe 9 heavier atoms, a single DFT calculation can take a whole hour of computer time.
An hour.
And if you're looking at something bigger, say 17 heavier atoms, you might as well just write off a whole workday.
Pretty much.
That's a huge bottleneck, isn't it? It just slows down discovery.
Exactly. It's like building with those Legos one tiny click at a time.
Yeah.
DFT is, well, it's essential for accuracy in many cases, but that computational cost, it really limits the scale, the speed of investigations.
Uh-huh.
And this is where the potential of machine learning and, specifically neural networks gets so exciting. The idea is basically to train computers on the huge amounts of data from these calculations and experiments.
Right.
So we can make predictions much, much faster.
So instead of painstakingly simulating every single interaction,
Yeah.
we're like teaching a computer to see the patterns,
That's it.
like showing it thousands of finished Lego sets so it learns the rules and can predict how a new one might turn out. And this paper focuses on a specific type of neural network for this, yeah.
That's right. The authors are looking at neural networks specifically designed to understand the structure of molecules. Because molecules, well, they're basically networks, right? Atoms connected by bonds. And what's really clever is using models that don't care how we label the atoms, the order we list them in. That's this idea of being invariant to graph isomorphism.
Okay, invariant, meaning it doesn't matter if you describe the Lego set starting from the front or the back.
Exactly. It's still the same set, same properties.
Yeah.
And models with that kind of understanding built in are probably going to be much better at predicting how molecules behave.
Which brings us, I guess, to the main topic, message-passing neural networks, MPNNs. This paper suggests this is like a unifying framework, a way to understand lots of existing work.
Yeah, think of it as a general strategy, a kind of master builder's guide, maybe,
Yeah.
that lots of different AI architects have been using for molecules. This paper helps us see the common ground, the techniques they're all using.
Okay.
And an MPNN basically works in 2 main stages,
Yeah.
a message passing stage and then a readout stage.
Message passing. Okay, that sounds like the atoms are sort of talking to each other. How does that work in the network?
Exactly. That's a good way to put it. During message passing, each atom has this internal state, just a bunch of numbers representing what it is and where it fits in. And over several rounds, these states get updated based on information messages coming in from their direct neighbors, the atoms they're bonded to.
Okay, so each atom looks at its neighbors and gets an update. What's in that update? What determines the message?
That's where the message function comes in. The paper calls it M. It's a learned function, a mathematical rule the network figures out. It looks at the current states of the 2 connected atoms and the properties of the bond between them.
Like single bond, double bond, maybe even the distance.
Exactly, things like that. Based on those inputs, it calculates the message going from atom A to atom B. Then, for atom B, all the messages it gets from all its neighbors are combined, usually just added up.
Right. And once an atom has collected all those messages, how does it change its own state?
That's the job of the vertex update function, or U, another learned function. It takes the atom's current state and that combined message it just received and calculates a new updated state for that atom.
And this repeats.
Yep, this whole process, sending messages, receiving messages, updating states it repeats for a set number of rounds, that lets information spread out, across the whole molecule network.
Okay, so information flows. Atoms refine their understanding based on their neighborhood. What happens after this information exchange finishes? That's the readout phase.
Precisely. The readout phase is where we take those final states of all the atoms and use them to predict a property for the entire molecule.
Like its energy, or how it interacts with light, or maybe even if it'll stick to a drug target.
Exactly, those kinds of things. And this is done using a readout function.
And the paper really stressed that this readout function has to be invariant to the order of atoms. Why is that so important again?
Think back to the Legos.
Ah,
Whether you list the pieces starting from page 1 or the last page, the final thing you build is the same, right?
Mm.
Well, a molecule's properties don't change if we just happen to list atom number 5 before atom number 3 in our computer file. So the readout function must give the same prediction no matter how the atoms are ordered. It ensures the whole MPNN respects this fundamental fact about molecules.
that makes perfect sense. Okay. And the paper then shows how several existing models, successful ones, actually fit into this MPNN idea. It's like discovering different dialects share the same basic grammar. Can you give us an example or two?
Sure. One early one they mention is convolutional networks for learning molecular fingerprints from back in 2015. Their approach basically combines info from a neighbor atom and the bond connecting them to make a message. Then it updates the atom based on its neighbors.
Okay.
But the authors of this MPNN paper suggest a potential issue. It kind of seems to treat the atom info and the bond info a bit separately, which maybe limits how well it can learn really complex relationships.
Interesting. So even early successes might have had slightly different ways of handling things, maybe limitations. What's another one that fits the framework?
Yeah. Another key one is the Gated Graph Neural Network, or GGNN, from 2016. This one uses learned rules specific to each bond type to transform the neighbor's information into a message. And for the update step, it uses something called a gated recurrent unit, a GRU.
GRU. I've heard of those in language processing.
Yeah, they're good at handling sequences. Here, it helps the model learn how to best integrate the incoming messages over the different rounds of passing. And a key thing about GGNN is it uses the same update rules in each round that's called wait tying.
Okay, so different strategies for how atoms talk and update. The paper also mentions things like interaction networks, molecular graph convolutions, deep tensor neural networks, even stuff based on the Laplacian. Wow, this MPNN framework really does seem to cover a lot of ground.
It does, yeah. Molecular graph convolutions, for instance, they update not just the atoms, but also the representations of the bonds during message passing.
Oh.
Deep tensor neural networks use more complex math tensors to combine neighbor info, and the Laplacian-based methods use graph theory tools to define how information spreads. The Kipfen-Welling model is a famous example there.
It's really cool how this framework gives a common language for all these different approaches. So the big question, what did the researchers behind this paper, Neural Message Passing for Quantum Chemistry, actually do? What were their main contributions here?
Well, their main goal was finding a really effective MPNN for chemistry problems, specifically focusing on this benchmark dataset called QM9. We can talk more about that.
Okay.
And one of their biggest achievements was developing an MPNN that basically set a new accuracy record on QM9. It could predict the results of those complex, slow DFT calculations we talked about.
Like the hour-long ones.
Yeah, predict them with amazing accuracy. They reached what's called chemical accuracy for 11 out of the 13 properties they tested.
Wow, chemical accuracy. That's like the holy grail, isn't it?
Yeah.
Getting predictions that are as good as or maybe even better than experiments.
Exactly.
Mhm.
It means the accuracy is genuinely useful for chemists, for materials scientists in practice. And they also did something really interesting. They built MPNNs that only looked at the basic connectivity, just atoms and bonds, no 3D shape info,
Just the blueprint.
just the blueprint. And even those models hit chemical accuracy on 5 out of 13 properties,
Mhm.
which is pretty surprising, actually. Predicting properties without the 3D shape is hard. It suggests the network is learning some really deep stuff just from the connection.
Like it's figuring out fundamental rules just from the structure itself.
Hmm.
They also mentioned, I think, a clever way to use more detailed atom representations without needing way more computing power.
Yeah, that's their multiple towers idea. We can
Yeah.
dive into that more. But the gist is they split the detailed description of each atom into smaller chunks, process those chunks sort of in parallel, and then combine the results.
Okay.
It lets them use richer information without the training time or memory use exploding.
So great results and finding ways to make these powerful models more practical. Now, you mentioned QM9 a few times. What exactly is that data set? Why is it such a standard?
Right, QM9. It's this widely used collection, about 130,000 small organic molecules. Think common elements: hydrogen, carbon, oxygen, nitrogen, fluorine. And none have more than 9 heavy atoms atoms that aren't hydrogen.
Okay, smallish molecules.
Smallish, yeah. And for every single one, researchers did high-quality DFT calculations to get 13 different fundamental properties.
And these properties cover a lot of different things.
Oh, yeah. Things like the molecule's energy, how it vibrates, its electronic properties, like how easily it gains or loses electrons, even how it interacts with electric fields. It's a really comprehensive profile for each molecule.
And critically, QM9 includes both the connections, the graph, and the 3D coordinates, so you can test models with different inputs.
Exactly. You can train a model that only sees the graph, or one that gets the full 3D structure. And QM9 also gives us those error benchmarks we talked about. We know the limits of DFT itself, and then there's this chemical accuracy target that everyone aims for. We want models to be at least that good.
Got it. So QM9 is this really important, tough test bed for these models. Okay, let's get into the specific MPNN variations they tried in the paper. What different message functions, ways for atoms to talk, did they explore?
They looked at a few main ones. One was that matrix multiplication method, like in GGNN, where the message depends on the sending atom's state multiplied by a learned matrix specific to the bond type.
Okay, and they also tried something called the edge network. You said that focuses more on the bonds.
Exactly. To handle richer bond information better, like the actual spatial distance, if you have it, they use the edge network function. Here, the bond features, like type and length, go into a small neural network first. That network outputs a matrix, then you multiply that by the sending atom state. So the message becomes a more flexible, learned function of the specific bond's details.
Makes sense. Instead of a fixed rule per bond type, it learns a custom rule based on the bond's features. What was the third message function?
That was the pair message. The idea here was maybe the message should consider not just the sender in the bond, but also the current state of the atom receiving the message.
Okay, taking the contact at both ends into account.
Right. So a neural network takes the states of both atoms plus the bond features to generate the message.
Interesting. Now, what about these virtual graph elements? Adding artificial connections, what's that about?
Yeah, that's a neat trick to help information flow across longer distances in the molecule, even between atoms that aren't directly bonded. They tried two main ideas: virtual edges and a master node.
Virtual edges.
Basically, you add an artificial connection between all pairs of atoms that aren't already directly bonded. And these virtual edges have their own learned properties. It creates shortcuts for information.
So even if atom A and atom Z aren't directly bonded, they can sort of pass messages via this virtual link.
Kinda, yeah. It helps information propagate globally.
Yeah.
And the master node concept.
Right. What's that?
That's a special artificial node, not a real atom. It's connected to every single atom in the molecule with a special type of connection. It's like a central hub.
A meeting point.
Exactly. Every atom can send info to the master node, and the master node sends info back out to everyone. It has its own state, its own updates. It helps capture global properties of the whole molecule.
Sounds powerful for long-range effects. Okay. And the readout functions, getting the final molecular property prediction.
They mainly use two. One was the method from the original GGNN paper, basically combining all the final atom states using some neural network layers.
Standard enough.
And the other was the set2set model. Set2set is specifically designed for handling sets of things, like the set of final atom states. It's thought to be potentially more powerful at summarizing all that information into one fixed-size vector for the whole molecule, which then feeds into the final prediction layer.
So set2set is maybe a more sophisticated summarizer. And you mentioned multiple towers earlier for efficiency. How does that work again?
Right, multiple towers. The idea is you take the vector representing each atom, its state, and you chop it up into several smaller vectors, the towers.
Okay.
Then during message passing, each tower gets processed independently, maybe with its own set of message update functions. Then after all that, you combine the results from the different towers for each atom back together using another network.
Like specialized teams working in parallel on different aspects of the atom's info. How does that save time?
Well, for some message functions, like the matrix multiplication one, the calculation gets much more expensive as the atom state vector gets bigger. By breaking it into smaller towers, the math for each tower is much cheaper. Even with multiple towers, the total computation can be faster and use less memory. And they also found some hints that this structure might help the model generalize better, learn more robust patterns.
Interesting. Like a committee of smaller experts. Okay, now what initial information did they actually feed into these MPNNs? What are the starting atom features and bond features?
For the atoms, they used pretty standard stuff: atom type, carbon, nitrogen, etc., often as a one-hot ejector. Atomic number, whether it's likely to accept or donate electrons, if it's in an aromatic ring, its hybridization state, how it bonds, and how many hydrogens are attached.
Standard chemical descriptors.
Yeah. And they also looked at whether making hydrogen atoms explicit nodes in the graph helped.
So actually drawing the hydrogens in the network.
Exactly. It makes the graph bigger, which takes longer to train, but for some properties, it might give crucial extra detail.
Right. And the bonds, how are they described?
They tried three main ways. Simplest was just the chemical graph, bond type single, double, triple, aromatic, discrete categories. To add distance info, they used distance bins. They just divided the possible bond lengths into, say, 10 bins and used the bin number as a feature.
A rough sense of distance.
Exactly. And then for message functions that could handle it, like the edge network, they used a raw distance feature. That was a richer vector with the actual Euclidean distance plus the bond type encoding.
So different levels of detail for the inputs. Okay, we have the models, the data, the inputs. How did they actually train these things?
They used uniform random search to find the best hyperparameters, the model settings you don't learn directly. The training itself used stochastic gradient descent, specifically the ADAM optimizer, which is pretty standard and effective.
Right.
They trained in batches, usually 20 molecules at a time for many, many steps. And the learning rate, how much the model adjusts itself, each step was carefully scheduled, usually decreasing over time.
And evaluating performance.
Yeah.
How did they know how well the models were doing?
Standard practice.
Mm.
Split the data. Training set to learn from, validation set to tune things and check for overfitting during training, and a final test set kept totally separate to get the real measure of performance on unseen data. They measured the error using mean absolute error, MAE,
Okay.
and they often reported it as a ratio. MAE divided by the chemical accuracy target for that property. So a ratio less than 1 means they beat the target achieved chemical accuracy.
Got it. So what were the big takeaways from all these experiments? What really mattered for getting good predictions?
A few key things stood out. First, for many properties, including detailed bond info, both type and distance really helped. And so did making hydrogen atoms explicit nodes in the graph.
So the richer input paid off.
It often did, yeah.
Yeah.
Also, interestingly, training one specialized model for each property usually worked better than trying to train one giant model to predict all 13 properties at once.
Huh. So specialization wins suggest predicting different properties might need different focuses?
Seems like it, yeah. Their absolute best MPNN used that edge network message function we talked about.
The one using a network for the bond matrix.
That's the one. Combined with the set-to-set readout and using explicit hydrogens, that combination got state-of-the-art on all 13 QM9 targets and hit chemical accuracy on 11.
11 out of 13, that's huge.
It really is. And they could even squeeze out a bit more accuracy by ensembling averaging predictions from their top 5 models.
Okay. And what about the experiments without the 3D geometry, just using the graph structure?
Right. In those cases, adding mechanisms for long-range communication became really important. Things like the virtual edges, the master node, or that set-to-set readout. They helped the network see beyond immediate neighbors.
Makes sense.
The set-to-set readout was particularly good there, getting them to chemical accuracy on 5 out of 13 targets with no 3D info at all.
That really shows the power of the architecture itself to learn complex relationships. What about the tower's architecture? Did it live up to its promise?
Well, the main goal was speed and scalability, but they did see some evidence it might also improve generalization, how well the model performs on new data. It seemed to outperform a standard GGNN, with set-to-set in some cases. But they noted that combining towers with their best message function, the edge network, wasn't straightforward and didn't immediately give better results in their first tries. So maybe more work needed there.
Right, still things to figure out in combining the best bits. Did they mention any other quick findings, like not sharing weights across time with the pair message function?
Yeah, briefly. They found not sharing weights, like in GGNN, didn't actually help performance. So the weight tying seems pretty solid. And the pair message function, the one looking at both atoms for the message, generally didn't do as well as the edge network, surprisingly.
Interesting. You'd think looking at both ends would be better, but maybe not always. Okay, stepping back. What's the big picture here, the main significance of this work?
I think the big takeaway is that MPNNs are a really powerful and flexible approach for predicting molecular properties. If you design and train them well, they can outperform older methods, get close to or even match quantum calculation accuracy, but way, way faster.
And the paper really highlights how important it is for the model to capture those long-range interactions across the molecule, right?
Absolutely. Whether it's through the core message passing or these extra tricks like master nodes or set-to-set, letting information flow globally seems key. And the towers idea offers a potential route to applying these methods to much bigger molecules eventually.
So where do we go from here? What future directions did the researchers suggest?
Well, a big one is generalization. Making models trained on smaller molecules work well for much larger ones. That's still a challenge.
Scaling up.
Exactly. And dealing with spatial info for large molecules is tricky too. The number of distances just explodes. They also suggested exploring attention mechanisms.
Attention. Like in language models.
Yeah,
Letting the network focus on the most important interactions.
precisely. Instead of just summing up all neighbor messages equally, attention could let the model weigh them, focusing on what's most relevant for the property prediction. That could really help with scalability and maybe even accuracy for complex
Yeah.
systems.
That sounds like a really promising direction.
Yeah.
Wow. This has been a fantastic deep dive into MPNNs and quantum chemistry. It's kind of mind-blowing how AI is tackling these fundamental science problems. It really makes you think about the future, doesn't it? Drug discovery, material science.
Yeah.
Could we be getting close to a point where we can sort of decode the rules of molecules just by training these sophisticated networks? What do you think that means for how we discover new things?
It's a profound thought, isn't it? The potential is huge. Being able to accurately and crucially quickly predict how any potential molecule might behave could just accelerate innovation across so many fields. New medicines, better catalysts, materials we haven't even dreamed of yet. This research is definitely a big step on that road, and it really opens the door to some incredibly exciting possibilities.